Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
So next topic is called as the semaphores. All right, the semaphores. So far we have seen that the hardware-based solution, which are trying to set a lock, unlock, etc. We call it as a hardware-based solution. Uh, to the critical section problem, right? They are actually complicated for application of programmers to use, right? Because you have to look at the bitwise whether there is a set or unset, the values of the lock is set, unset, etc. etc. have to be discussed, have to be seen first before you program it properly, right? So to overcome that difficulty, there is another synchronization tool that we can use is called as a semaphore. Okay, so first let's write the critical section problem solution using hardware solutions are slightly difficult. Okay, the critical section problems solution, all right, by using the hardware based approach. Is complicated for uh, programmers, right? So we have another synchronization tool, right, called semaphore. Okay, to overcome this, we can use another synchronization tool called semaphore. Okay, now let's look at our semaphore. Normally the semaphore is denoted by capital S. Okay, so I'll write here S. So S is usually going to be a integer variable, right? Apart from the initialization, right, it is accessed only through some very standard operations. One is a wait signal and another one is called as a signal. There are two processes. One is a wait process and one more is called as a signal process. Two processes are allowed to examine the value of this variable S at any given point of time. Nobody else can check this. That's one very basic condition, right? Initialization can be done anywhere. You can use a process to initialize the value of S, or you can write a simple code to do that, or simply you can initialize anywhere in the code, right? Initialization is possible anywhere, but who can access, right? It can be accessed by only two types of standard operations or standard processes, right? Namely wait and signal. So let's define what is this S. All right. A semaphore, capital S, is normally an integer variable. It's going to hold the integer values only. Okay. So other than the initialization, because initialization can be done by anybody, anyone. All right. So other than the initialization, uh, it it can be accessed only by two standard operations called, one operation is a wait and the second one is signal. You have a wait and signal. All right. Okay. Now let's look at what are the jobs for wait and signal. Okay. The wait, right, is used to test. You are supposed to test something. Okay. Normally some of the books will call it by the name P. The process P is actually a wait operation. Okay. At the same time, you have another process, that is the signal. All right. So the signal is used to uh, increment. So some books will call it by the name V. One is for P, one is for V. Okay, you are going to increment something. Okay, now let's see how they are defined normally. Right, the general definition of wait signal we'll see now. General definition of wait. So this is the process wait of S. S will be the semaphore. This is equal to say we use a while condition, while S is less than or equal to say 0, do nothing. So this is, you can call no operation. Otherwise you keep decrementing S. Alright, so we'll look at the details later. Let's define them first. So that's the general definition used for wait function. Then let's try to define general definition of the signal. So we declare this is signal of S. So here simply perform S++ and you come out. So we can see that the S value is accessed by both by both weight and as well as the signal, right? So I'm checking something in the weight condition. That's why we called it as to test. We use that particular operation to test something. What you are testing while S is less than or equal to 0. That's what we are testing there. If that's not the case, right, you simply keep decrementing it. Okay. Whenever that condition is met, you don't do anything. No operation. Whenever that condition is not met, you right decrement S and come out of the weight function. Okay. Similarly, the signal function is going to perform right to increment, as the name suggested over there. We called it as right. So we checked there, right. The signal is used to increment, right. So we have to show the increment. That's what is being done here. It's incrementing our function. The value of S is being incremented. Okay. Now, all the modifications to the integer value of a semaphore, right, in the weight and the signal operations, right, must be executed, right, individually, right. When one process modifies the semaphore's value, no other process can simultaneously simultaneously modify the semaphore value at the same point. This is important, right. In addition to this, uh, say in case of the weight, the testing of the integer value of s less than or equal to 0, and maybe a modification s minus minus must be executed without any interruption. And somebody is using the weight, somebody else cannot use the signal. Okay, so how these operations are implemented we'll see after this, but what are the conditions to be met, we are actually discussing those points now. Okay, so let's write that now. So semaphores definition we are looking into, right. So let's write that point. All modifications to the integer value of the semaphore s. In first one is weight and second one is signal operations must be executed. We can call it a indivisibly, sorry, indivisibly. In the sense, the meaning is that when one process modifies the semaphore value, no other process can simultaneously modify the semaphore's value. Okay, this is what we need to take care of. All right. In addition to that, right, when let's say that it's the process is what we are executing here is s. Weight is being executed. So we'll write that point. In weight of s, in that process, the testing of s less than or equal to 0 and its possible modification. What is a possible modification? In bracket I write s minus minus, right, must be executed without interruption, because if somebody else will modify the value of s at that point, right? You have problem. This must be executed without interruption. So these are the conditions, right, that we have to take care whenever we use the semaphore. Okay, right. So now the next concept that is coming under semaphore is how do you use this semaphore? Okay, so next side heading that I'm going to write here is using semaphores. So what are semaphores we defined in the previous section. Now we'll see how the operating systems use semaphores. Now basically the overall idea is that OS has two types of semaphores being used. Okay, first one is called as a counting semaphore and second one is called as a binary semaphore. All right, so in OS we see two types of semaphores. OS, so there are two types of, I'll write S. Okay, so two types of S. First one we call as the counting semaphore. Counting S, counting semaphore, and another one you call it as the binary semaphore. So right, you don't have any restriction, it's just used for counting, right? So I can write here this can range over an unrestricted domain. In a sense, it can take any values, right? S can go because S is an integer, right? S can take any value. But when it comes to the binary, right? We know that binary can range 0 and 1, right? So range only between 0 and 1. Okay, so the same definition may look differently in a different textbook, right? So normally binary semaphores are also called as mutex lock, right? So locks are, in the sense, lock is either two states. Locks will have two states, lock or open, right? Maybe a lock is indicated by 1 and open is 0, or the vice versa. So I just write here that name, this is called as mutex locks. In some textbooks and some systems will follow this kind of notation. All right, now the usage of these binary semaphores are normally dealing with the critical section problem for multiple processes, right? So whenever you have n different number of processes sharing a single semaphore, right, normally initialized with the value, each of the process is organized in a specific fashion. Okay, so let's look at the fashion now. Let's define it. Binary semaphores can be used to deal with the critical section problem. For multiple processes, right? For example, let's consider the number of processes to be n. Okay, so the n is a number, n processes share uh, a semaphore. Since it is binary, you see the name itself will suggest that this is a binary. You don't have to say that, okay, you don't simply define this semaphore as s, because s can take any value. But if you want to make sure that somebody who is looking at the name of the semaphore, he should be able to identify that, okay, this is a binary semaphore. What you can do, you can give a name like mutex itself, because mutex has a meaning. You have 0 or 1, correct? So let's say the share a semaphore called, let me define it as mutex. Okay, uh, let's initialize to 1. Its initial value is 1, right? And now we say that each of the process pi can be organized as follows. Each process pi can be organized as, let's try to define each of the process. Okay, now that is, let's go to a do statement, and then I write I call a function weighting of mutex. All right, then followed by this, I will write the critical section. Okay, after the waiting part, execution of critical section will take place. Once the critical section has been covered, now we go for the signal. Okay, signal of, after this, right, we know that we have another part that is coming up, that is remainder. It will follow, right? After the remainder section gets over, we'll close and we'll write while condition. This is while, maybe it's always true. Right, now this whole concept should help us in understanding the mutual exclusion part, right? Anyway, so irrespective of what method you use, you can use a lock open phenomenon, or you can use a true or set of a bit, that technique, or you can use a swap, you can use semaphores. Irrespective of that, our intention is to overcome the basic issue of critical section. Now I need to prove that, okay, even if you use the semaphores, you are still able to meet the 3 requirements. Okay, first one we'll discuss now. Okay, so now using this technique, we are supposed to overcome the synchronization problem. We'll come to that exact explanation later. So one of the idea is that if you have a binary semaphore, you go for a weighting part. The weighting will do what? It will check some condition, right? It will check some condition, and then if at all that condition is set, right, it will do nothing. It will come out, it will simply execute the critical section. Okay, But if the condition is not met, if you can see that, it will decrement, correct? It will decrement the S value. In this case, it is mutex. All right. So mutex value, depending on that, you can actually check this. Right. That's the first thing. Now, the other semaphore, this is the first semaphore. First type of semaphore is we discussed now is the binary semaphore, binary S or the mutex. The next one we can see here is the counting. Okay, so we'll look at the properties of counting now. So if you have a counting semaphore, right, we can use to control the access to a given resource consisting of finite number of instances. Whenever you have, right, a resource with finite number of instances, you can allow, right, somebody to enter into that or somebody who should not enter into that. You can decide that using the counting semaphore. Okay, so let's just look at the outline now. So this is just the introduction to two types of semaphores, okay, that actually exist now. So using the, if you want to use the counting semaphores, one can control the access of a resource with finite number of instances. So normally you can initialize the semaphore with the number of resources available, right? So you have 10 resources, you initialize, right, the value of semaphore as 10. Each process that wishes to use a resource performs this wait operation, because wait performs what? You can see that wait will decrement the number. I actually have 10, so somebody is using it, it will be reduced, right? Somebody else is using that particular process will further reduce the value of S. So you can see that when a process releases the resource, it can perform the signal operation because signal is increasing. Correct. So that's how the counting semaphores will work. We'll write one or two sentences over here. Okay. Uh, this semaphore can be initialized the total number of available resources. That's the first thing. Whenever a process uses a resource, will perform the wait operation. If a process uses the resource, it first performs the wait operation. Okay, right, because you are actually decreasing the count inside the wait, you are decrementing. All right, now if a process releases the resource, then what is required? It has to perform the signal operation. It simply performs the signal operation. So we know that in signal you are using the signal to incrementing something. So now you see the idea. When the count of the semaphore goes to 0, all the resources are being used. So after that, if at all a process wishes to use the resource, will be blocking until the count becomes greater than 0, right? Because if it is less than 0, do nothing. You say that you are doing nothing over there. It will be inside that particular do nothing, the semicolon part of your code. Just check over there, right? So it will do the no operation. Whenever while s is less than or equal to 0, it's always in that loop only. Why? It will be within the while loop, right? So what do you mean by do nothing? It's actually blocking the whole process, right? It will not be allowing the particular process to execute. It will be within this loop. When s is less than or equal to 0, it will be within this. Somebody releases the resource, means this s will become 1 after that, because s is equal to s plus 1. So in that case, this condition is not satisfied and you go further. Somebody will take that resource, s will be made 0, and that it will come out. Okay, so that's how this particular usage of counting semaphores used in OS. Okay, so let's write that part now. Okay, so that means if count for any semaphore goes to 0, this means all resources are being used. So when that happens, if a process that wishes to use a resource will be blocked, right? This implies all other processes who want use the resources will be blocked, right? Until what? Until when? So we have to tell until when. So until the count becomes greater than 0. Until the count becomes greater than 0. Okay.
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.